Hello and welcome again to my Physics Online video lecture series. Today's video is a follow-up or an addendum to my previous video about energy conservation. We previously just discussed the ideas behind energy conservation, kind of where it comes from, and then I ended with a sort of conceptual example with a wiggly ramp and a block sliding down the wiggly ramp to crash into a spring at the end. I never really worked an actual example, however, and so in this video I'm wanting to work through an example for you all. So let's say that I have a block and I've put it at the top of a 6-meter long ramp. The ramp is straight in this case, and it's at an angle of elevation of 10 degrees. And then at the bottom of the ramp we've put this ideal spring which is attached to a little platform that this mass can basically like butt up against and compress until it stops. So we will assume that the spring is long enough that the mass will just be compressing it until the system is at rest. And so our question is, how far does the spring get compressed before the block comes really to rest? So how do we go about solving this problem? Well, we can use energy conservation. So energy conservation in this case says that the kinetic plus the potential energy initially and the kinetic plus potential energy finally must be equal to each other. There's no friction, so there's no outside force to do any work on the system, so hence I have not included a term there. Now initially I have this block at some height above the sort of like final position, and it's at rest. So initially I have 1/2 mv initial squared, but that term is 0, plus mgh. And then finally I have 1/2 mv final squared, but that's also 0 because it ends up at rest. I have m times g times 0, so obviously that's 0. And I have a compressed spring, 1/2 kx squared. So I should be able to just solve this equation for how far the compression is. X equals 2 mgh over k square rooted. But, and here's where the interesting wrinkle to this problem comes in, I didn't actually give you guys a height. I gave you a length of the ramp. So we need to extract a height from this length of the ramp. And I can label all the other terms in here if I want. Here's the mass, here's the k, this right here is a length. This right here is an angle theta. So we ask, what is the height of the ramp? And the answer is, well, this ramp basically makes this nice triangle, or part of a right triangle, in which I have this 10-degree angle of elevation and I have a 6-meter long ramp. So the height goes with this side. So we ask, how is this height related to this length of ramp and this angle? And the answer is, the sine of an angle theta should be the opposite side divided by the hypotenuse. Okay, therefore it follows that the opposite should be the hypotenuse times sine theta. So the height h, don't confuse height h for hypotenuse h, the height h should be the length times the sine of theta. And so that's 6 meters times sine of 10 degrees if you want it. So you could calculate what that is. You could also just plug it in over here. So this becomes square root of 2 mgl sine theta divided by spring constant k. Okay, and now we can plug some numbers in to our equation. Again, we have all the numbers. We have an m, we have an l, we have a k, we have a theta. G is 9.8 meters per second squared. So you have 2 times 4 kilograms times 9.8 newtons per kilogram times the length, which is 6.0 meters, times sine of 10 degrees, all divided by the spring constant, which was 80 newton per meter. If we plug everything in to the calculator to get a value out, divide by 80, and then we take a square root, I get 1.01 meters. So that's, if I plug everything in, 1.010470823 meters. And of course, we don't want to keep so many significant figures. We probably want about 2 in this particular problem. So the compression of the spring is about 1 meter for this set of parameters. And that's all for this little demonstration, this little video. You are welcome, of course, to tinker with it yourselves. For example, what would happen if we added some friction, either by specifying the force friction present or by specifying a coefficient of friction. But I'm not going to do that in today's video. Instead, I'm going to sign off and say thanks for watching.